All right, this is lesson 3 of chapter 2, Dynamics in Physics 30. So we're going to start talking about forces of friction. Friction is a drag. It always works against you. We have two different types of frictions. We have static friction, which is the forces that must be overcome in order to start an object moving. So static friction is what keeps something in place. And then there's kinetic friction, which are the forces that must be overcome in order to keep a body moving. So static friction is what is experienced when an object is just sitting in place, and kinetic friction is what is experienced when an object is actually moving. So think about like the friction on a carpet if you're dragging one of your siblings across it. Static friction is always greater than kinetic friction, meaning it takes more effort to get a body moving than it does to actually keep that body moving. So we end up with these two equations. We have the force of friction is equal to mu k. Mu is a Greek letter, mu k, meaning the kinetic friction coefficient, multiplied by the natural force. Um, this force due to friction will be less than or equal to mu s, which is the coefficient of static friction multiplied by the natural force. Here we have a table of general coefficients of friction, which we don't need to refer to too much, so we're going to skip over this pretty quick. And another similar one. So for example, when you have wood dragging on wood, you've got a coefficient of static friction somewhere between 0.25 and 0.5, whereas your coefficient of kinetic friction is only 0.19, meaning that it's going to take less force to keep that wood on wood moving than it will to initially get it started. And you've probably experienced this pushing some kind of heavy box around or moving furniture or whatever. It takes more effort to get that thing to start moving and less effort to actually keep the object moving. So here's an example. It takes 20 newtons of force to keep a 4 kilogram block moving at a constant speed across the floor. Calculate the coefficient of kinetic friction. Now here's something that might seem a little counterintuitive. A block moving at a constant speed means there is no acceleration. Um, if an object is sitting still, as soon as it starts to move, that means there's been acceleration. So saying that an object is moving at a constant speed means there's no acceleration. So either that could be a constant velocity, or it could be, and this is what is more often, a constant speed of nothing, meaning because there's no acceleration. So often in these questions, when they say a constant speed, they really mean the object is sitting still and not actually moving at all. So we need to calculate the coefficient of kinetic friction. We know that the applied force to have this object moving forward is 20 newtons, and in the opposite direction we will have the frictional force working against that. Now, because of this key wording, constant speed, we know the object isn't actually moving. So that means these two forces going right and left have to be perfectly balanced. Otherwise, there would be acceleration in one direction or the other. So therefore, we know that the frictional force is also 20 newtons. We, of course, have the gravitational force pulling down and the natural force pushing up. Now we know gravitational force is equal to mass times acceleration, the mass being 4 and acceleration of gravity being 9.8. So therefore the force of gravity is 39.2 newtons. Now we also know that the natural force is going to have to perfectly balance this. So that means natural force is also 39.2 newtons. Recalling our equation, we have the force due to friction is equal to the coefficient of friction multiplied by the natural force. Now, since we're looking for the coefficient of friction, we can just divide both sides of this equation by the natural force to give us that the coefficient of friction will be equal to the frictional force divided by the natural force. Luckily, we both know both of those numbers. So we know the frictional force is 20 and we know the natural force is 39.2, so we can simply divide them and we find that the coefficient of friction is 0.51. Now, hopefully you've already watched the video on the note about angles on an incline using g sine theta and g cos theta instead of actually the force of gravity, and that's important for these angle questions. If there is no friction, we have that gravity, the acceleration due to gravity, is simply gravity multiplied by sine theta. Whereas if there is friction, then the acceleration due to gravity will actually be gravity times sine theta minus the coefficient of friction multiplied by gravity multiplied by cosine of theta. So these are two key formulas that you will find on your formula page. An example, well, not really an example, a thing that leads us to a formula. At what angle will an object begin to slide? Well, it's going to begin to slide when the force of friction is equal to the coefficient of friction multiplied by the natural force. As soon as it overcomes that, and the force is greater than the force of friction holding it in place, the object will begin to slip. Now, we know that the force of friction, or any force, is mass times acceleration, and we know that acceleration can be replaced with g sine theta. So therefore, we can replace the force of friction with mass times g sine theta just standing in for acceleration. And on the other side, we have the coefficient of friction multiplied by the natural force. Natural force would be, again, mass times acceleration, which from our other video we know is g cosine theta. So this equation actually works out to be mass g sine theta equals the coefficient of friction times mass g cosine theta. This is kind of convenient because that means that the mass and gravity will cancel out from both sides, meaning we have sine theta is equal to the coefficient of friction multiplied by cosine theta. So dividing both sides by cosine, we get that the coefficient of friction will be sine over cos, which you might remember is just equal to tan theta. So an object will start to slide when the coefficient of friction is equal to the tan of the angle. Now it's important to note that because the masses canceled out, that means this will always be true regardless of the mass of the object. And so we end up with a picture that looks like this. We're not really going to be using the gravitational force much at all. This one down here, we're not going to really be using this because this direction does not help us. We're going to be using gravity instead to calculate this mass times g cosine theta because that counteracts the natural force. And we're going to be using it to calculate mass g sine theta because that counteracts the applied force. We like these things to work contradictory to each other. So, an example, we have a skier here skiing downhill at 30 degrees, and we are told that the coefficient of friction is 0.18. If there is no friction, well, then we simply have acceleration as g times sine theta. So that would be 9.8 times sine 30, which will give us an acceleration of 4.9 meters per second squared. With friction, we have the lovely formula A equals g sine theta minus the coefficient of friction, g cosine theta. So plugging in everything we know, we get acceleration will be equal to 9.8 times sine 30 minus that 0.18, which is the coefficient of friction, multiplied by 9.8 cosine 30. Calculating all of that out, we get an acceleration of 3.4 meters per second squared, which should make sense that if there's no friction between the skis and the slope, he would be accelerating faster than if there is friction between the skis and the slope, in which case the skier will be accelerating slightly slower. One more example. we are asked what is the force on each connecting rope. The only thing we know about these forces right now is that the force on the first rope, the one actually being pulled, is 12 newtons. A key point in this example is that because these objects are all tied together, overall the whole system, all three objects, will be accelerating at the same rate. So looking at force 1, we know that force is equal to mass times acceleration. And the total mass being pulled by that rope is all three objects, the 1 kilogram, 3 kilogram, and 2 kilogram. So we can add them all together, and we'll get that that force of 12 newtons is equal to a mass of 6 multiplied by the acceleration. So therefore, the acceleration is 2 meters per second squared, meaning this whole system is being pulled forward at 2 meters per second squared. We can use that then on the second force of the rope, which is still mass times acceleration. However, in this case, this second rope is only pulling the two objects behind it. It doesn't have the weight of the 1 kilogram object on it. So its mass would simply be the 3 and the 2, and we know already the acceleration is 2 meters per second squared. So the force here would have to be 10 newtons. Applying the same logic to the last rope, this one, the only mass here being pulled by it is the 2 kilogram object, and we know that its acceleration is also 2 meters per second squared because everything has to be accelerating at the same rate. So we can plug in both of those 2's, and we get that the force on the final rope will be 4 newtons.